Hello, and welcome back to some coding. And we're going to code our very simple convolutional neural network to classify digits. So in this problem, the data that is given to you, before we move on to the code, it's important to understand the data bit. And the data that we are given is, we've got an input image, and what we have is at the corresponding is a label, whether this is 0, whether this is 1, 2, up to 9. So we have got a 10 class classification problem that we are trying to solve. The input is an image, it's a single channel image, or what we call a grayscale image, which can have like 7 written over here like this. And we want to make a neural network that takes this input image and produces the corresponding label at the output. So the number of neurons in our output is going to be 10, one corresponding to each of the digits. And we are going to design a convolutional neural network to solve this problem. So this is how you can solve a convolution neural or make a convolution neural network in PyTorch. Keras, in Keras it's easier, so I'm not going to discuss that. I'm just going to give you a link on how it can be done. But let's try to understand what happens here. Always remember representation, evaluation, and optimization. In terms of the representation bit, the first thing we need to do is to describe how a neural network takes this input image and produces a corresponding output. So that's what we're going to do. This is the constructor or the pseudo constructor of this neural network. We have a class that is derived from this nn.module of PyTorch. And then what it does is, first of all, we need to put all the layers or all the type of neurons that we want in our neural network. And that's what we are going to do. We are going to have two layers of convolutions followed by a fully connected layer. Okay? And let me walk you through what this neural network is going to look like. It's going to take an input image of a certain size, which is, I think, 28 by 28 in our case. Okay, so that's an input image that is going to go in. It's going to go to the first convolution block. Okay, and I'm going to talk about what that convolution block is. And the output of each of these is then going to go into the second convolution block. And then that output is going to be fed into a fully connected layer that is over here. And then that fully connected layer is going to produce our desired output. So I'm going to call it fully connected over here, or dense layer. And that is going to produce an output. Okay, so that's the rough structure of what we are going to do. If you look at it, the first layer, the first convolution block I call C1, over here it's called layer 1, is a sequential block, just like any other convolution model that is only feed forward. This is also a feed forward model, or a sequential model in this case. It takes an input image of a single channel, that's why this is 1, and it applies 16 filters on that image. Each of those filters is going to have a size of 5 by 5. Each of those filters is going to move by a step of 1, and at the output of each of those filters we are going to pad the surrounding areas where we run out of the border. When we are applying convolution, we are going to pad those by 2 pixels, which is, if you think about it, simply half of the size of this, because that is how much we'll fall over the edge at each convolution output. So this is going to have 16 convolution filters. So this has 16 filters with a stride of 1 and a kernel size of 5. And I welcome you to calculate what is the number of images that we are going to produce at the output. So we have got 16 filters which are being convolved with a single image. How many images do we get in the output? If you want to pause here before I answer this question, that would be great. You must have figured out that since we have a single input image and there are 16 filters over here, the output is going to contain 16 images. But what the next question is, what is going to be the size of each of those input images? That can also be calculated. If you have got a 28 by 28 image and you're trying to convolve it with a single filter, which is going to be of size 5 by 5, which is specified over here by specifying the kernel size, we can calculate what is the size of that image going to be. And that is really easy. I welcome you to pause the video and calculate that size. The way we are applying this convolution is that we have a stride of 1. So it's going to produce an image of size 28 minus 2, which is going to be 26 by 26. Okay, so we are going to, as a matter of fact, I think I've made a mistake over here in this calculation. There are going to be 2 rows and 2 columns on each side that are going to be dropped. So this is going to be 24 by 24 probably. You're welcome to verify that in your hand calculations as well. And once you have this, we have a padding here over here as well. So this is going to fall back to the same size as the input, as the original input. So it's going to produce an output of size 28 by 28 as well. Then what we do is we have something over here called batch norm. For now, please ignore that. We are going to come back to this in a bit, in just a bit. Okay. The next thing we do is we apply a rectified linear activation function on the output of each of those pixels in this image. And then we apply a max pooling that is going to be of size 2 by 2. Remember, we talked about max pooling. So what that means is that if you have got an input image that has, as a matter of fact, we can just go back and take a look at that image. So let's say if you have got an input image of size, in this case 4 by 4, okay, and you apply a max pooling of 2 by 2 with a stride of 2, then the output is going to be this thing. By stride, I mean, first of all, let's talk about the size of the max pooling kernel. If your max pooling kernel is of size 2 by 2, then what that means is that you can have the max is simply applied in a 2 by 2 square on this image. So if this is the convolution output, then with a max pooling of size 2 by 2, you're going to end up with having 20 over here, because that is the max of these 4 numbers. And because our stride is 2, then we are going to move this max pooling filter, or this max pooling block, by a size of 2, and then the next max pooling that we are going to do is going to be over this bit, and that there the maximum value is 30. So that's what we are going to use. We can then move down, and then we are going to produce 112, and then we have, if we move by 2, we can have 37. So essentially we're going to reduce that big number into a smaller number by a big matrix into a smaller image by simply doing this max pooling. I welcome you to think about what would have happened if we had used a size 1 by 1, if we had used a stride of 1 in this max pooling bit, or if we had used a different size for the max pooling block. Okay, so if you come here, what you get is, in this case, we have used a kernel size of 2, and you have used a stride of 2, and then that is going to give you an image at the output. The only thing that we haven't covered so far is what does this batch normalization thing do, and we're going to talk about that in just a minute. Or perhaps we can discuss that when we discuss batch normalization in detail. For now, you can perhaps even ignore this, and you can just continue or not add it to your neural network. Doesn't really matter much, at least at this stage. So once we have understood that this convolution block is going to produce an output of a certain size, it is going to have a number of images. If you have a single channel as the input image, the output image is the number of channels in the output image is going to be equal to the number of filters you have. So the output that we are going to get is going to be 16 different matrices, each of a certain size. So that's why we have, in the next convolution block, we put 16 over here, because that is the number of channels that this particular layer is expecting. We apply 5 by 5 convolution over here as well, but this time we have a stride of 1 and a padding of 2. So essentially a copy of what we had above. We do that again. So we have our first layer and we have our second layer, and then whatever the output of that is, which is going to be, in this case, since we had 32 filters over here, it's going to produce an image of size 32, and then that is going to go as input into our next multi-layer perceptron block, which is going to be a fully connected one, and there we are going to simply produce an output. So this is the structure of your convolution block. There's an important thing over here, and that's really important to understand, in the sense that the second convolution block that we have accepts 16 images as input, not the original images. It is the convolution output of the previous block. So when C1 or the first layer acts on this convolution or on this image, it produces a 16 channel image. That's what I mean over here. And then that 16 channel image is going to, each of those 16 channel images is going to go through convolution with a filter which is of size 32, but sorry, the number of filters is of there are 32 different filters, each of size 5 by 5, and then that means you're going to get 32 channel image at the output, which is the convolution output of these filters as input. We can connect this. This is the connectivity. This function describes the connectivity. You have a single input image. You pass it through the first layer. You pass the output of that to the second layer. You reshape it or you flatten it, and then you can connect it to, you can pass this to the output, and then you can return the output. So this is the representation bit of our neural network here. The next bit is, of course, evaluation. And what we have is a 10 class classification problem. So we solve that by minimizing the loss between, for a given example, between the outputs and the labels. We can use a loss function such as cross entropy, and I welcome you to explore what this means exactly. It essentially measures how far away your predictions are from your targets. And for a given set of input images, we go through each of those epochs. We have a train loader that loads a certain set of images into the memory of the GPU. So this is simply transfer of the data to GPU. We pass those labels as well. For a given set of input images in the batch, we compute the output. Okay. And once we have computed the output, we compare that output to the labels, we compute the loss. So this is the evaluation bit of our machine learning model. Once we have that, we simply do a back propagation or the optimization over here. And once we have optimized that, we can continue doing that for multiple epochs. Each of the epochs is a single instance of the neural network taking a look at all the examples in your training data, and we can keep on repeating this process until we have convergence. We can plot the convergence, and once we have done that, we can generate predictions. And this bit over here, model.eval, is really important, and this specifying torch.nograd is also really important because our neural networks use batch normalization. If you haven't used batch normalization, and I know we haven't talked about it just yet, but if you do, it's really important that you always specify this. This is a common rookie mistake, and which can mess up your testing. So it's important that you do that. Within the testing, you can pass your training data to the GPU. That's all this is doing, and you can pass your images to your model, which now generates an output. You can compare that output and you can calculate the test accuracy. You can even go ahead and save the model if you are satisfied with it. So this is the complete cycle or the life cycle of your neural network in PyTorch. Remember, we start off with a classification problem. In this case, it was a 10 class classification problem. We create a convolution neural networks which can have one or more convolution blocks, such that the output of one of the convolution blocks feeds into the next one, and so on. And what happens at the end is you pass the output of those convolution blocks through pooling and through flattening, and then that is passed to a fully connected layer, which in our case was only it had 7 by 7 by 32, which is the size of the flattened output from the convolution block, and then that is passed to your output layer. So it had about 7 by 7 into 32 at the input, and then it produces a 10-dimensional output. So the number of layers is simply a product of these two numbers. Okay, and then that allows you to compare it with your output, and you can do learning. So this is how you can implement a very simple convolution neural network in PyTorch. I posted the link to the code that has been used over here, and you're welcome to explore it on your own. The good thing about PyTorch is you can stop the execution at any point. So you can insert breakpoints, unlike the earlier version of TensorFlow, where you had to compile the whole neural network and then try to see what the neural network is doing. The debugging bit was a bit difficult, But in PyTorch, you can simply stop this execution at any time. You can look at what your data currently looks like within the neural network, and that's huge, in especially when you're trying to construct different types of neural networks and you have or you're starting off in it. Okay, so in the beginning, I would expect that Keras would be the easiest way for you to do your assignments and your build simple neural networks. But once you are past that threshold, PyTorch gives you very fine-grained control over what you want to do, and you can stop your execution at different stages, find what is the dimensionality of your data. It's pretty powerful machine learning library. Okay, and you don't need to even write the whole of the optimization problem mathematically or implement gradient descent by yourself. It automatically has different type of optimizers built into it, and you can use those. In this case, we're using an Adam optimizer, and we optimize all the weights in the neural network, which are specified in model.parameters with a certain learning rate. Okay, thank you.